Yeah, so I'm going to be talking about sources of uncertainty in simulations of Arctic sea ice in climate models. And I will follow that on with some implications for model development needs. And so you can see there's sort of a cast of characters here. I'm going to show results from a number of different studies. A number of people have contributed to those, and I actually have references at the end if people are interested. Okay, so there's been a lot of work done looking at uncertainties in climate projections and what the sources of those uncertainties are. And so we can track it to basically three different characteristics of our climate simulations. So there's internal variability, which just arises from the internal climate dynamics. There's a model structure, of course, the fact that our models aren't perfect, we have different parameterizations, different resolution, et cetera. And then there's scenario forcing, the fact that we don't actually know what emissions of greenhouse gases and aerosols will be in the future. So there's been a lot of work looking at these sources of uncertainty in climate projections. This shows one example from a recent study looking at uncertainty in September Arctic sea ice cover. So what you see on the left is a time series from six different multi-model, large ensembles. So the colored lines are individual large ensembles from individual models. The spread around those lines are basically the spread across the large ensembles. And this is showing the percent of sea ice remaining in the Arctic Ocean from those different model simulations. The dotted lines are showing the CMIP5 multi-model ensemble means for different scenario forcing. So we can basically take all of this information, which includes hundreds of years of model simulations from many different models, and quantify that into the fractional contribution of these different sources. And what you see is that internal variability is quite important on the near term, the next several decades. Scenario uncertainty, basically our uncertainty in what the forcing will be in the future, kicks in around the middle part of the 21st century, and model uncertainty in the blue is important across timescales. So this is what you see for sea ice. It's what you see for other aspects of the climate system as well. So that shows in terms of climate projections. We also have looked at sources of uncertainty in our historical climate simulations. And just showing two examples here, this shows kind of the importance of internal variability when you're looking at decadal scale trends. So I'm showing the histogram of September extent trends for two different time periods, the 1920 to 1940 time period in blue, and the 2000 to 2020 time period in black. And these histograms are from the CESM 1 large ensemble, where we have many different realizations of what the climate has done over time. So you can see that, there's a shift in the distribution, but these distributions are very wide. Kinds of trends that we see in the observed system. There's also, of course, been work looking at the influence of model structural uncertainty. And so this right-hand plot shows the September Northern Hemisphere sea ice sensitivity to global mean surface temperature. So it's just the change in sea ice area per change in global mean surface temperature for this 1979 to 2014 time period for two different models, the CESM 1 large ensemble and the CESM 2 large ensemble. And you can see that the sensitivity, there's of course this wide range. So the box and whiskers are just the interquartile and full range across the ensemble of simulations we have. So internal variability, again, is very sizable. But there's also a definite shift in the model itself. So you might attribute that difference to a model structural difference. But if you did so, you'd actually be wrong. And the reason is that the forcing has also changed between these large ensembles. And so I think another aspect of historical Arctic sea ice and our simulations of historical Arctic sea ice that's perhaps less appreciated is that we also have a great deal of uncertainty in what our historical forcings were. So what I'm showing is anthropogenic and biomass burning aerosol emissions that were applied in CMIP5 in the red and CMIP6 in the black. And so post 2015, these are our differences in forcing scenarios. we expect those to be different. Those are not the same scenarios. But prior to 2015, these are supposed to be based on observational records. And you can see that prior to 2015, these also differ considerably. And that can have implications for how the climate is simulated. And they differ because we're uncertain about what those emissions were. We don't have good observational records in a lot of locations. So this shows the global mean. You can see there's offsets in the mean, for example, for the secondary organic aerosols and others. We also find that there's considerable differences in variability in terms of the forcing. So this shows an example of that. This is biomass burning emissions for the 40 to 70 north region and globally, as applied in CMIP 6 in the black and CMIP 5 in the gold. What you see that, is that during this time period from 1997 to 2015, the biomass burning variability in CMIP 6 ramps up enormously. And that's because satellite emissions, satellite-based emissions were used during that time period because they were available. So they're more realistic, but you also get this weird change in the variability of the emissions that we're using to force our climate models. You can see in CMIP 5, those weren't included. It was very smooth. And so there's this difference not only in the mean state, there's a difference in the variability, there's a difference in variability and how it changes over time. All of these things have implications for the simulations in our model. And we find that in this recent paper by Patricia de Repentigny et al., that change in variability, there's nonlinear cloud aerosol interactions that mean that you don't get the same response if you use a smooth emission over that time period. And I'll show some results on that. Okay, so we basically wanted to ask a simple question. What is the influence of model structure and forcing uncertainty on historical Arctic change? So I'm going to just focus on the forced climate signals, so just ensemble means from large ensembles of simulations. And I'm going to do this within the context of just two models, the CESM2 model and the CESM1 model. And I'm going to look at the uncertainty inherent in forcings by looking at CMIP 6 versus CMIP 5. So CESM has these large ensembles that have been run. And we've run those for both our CESM1 model and our CESM2 model. So within an ensemble set, all of those simulations, we have numerous simulations. All of those are subject to the same external forcing among those two sets. And we just have small perturbations in the initial state because the system is chaotic. They then evolve differently over time. So we can, attribute the forced response to the mean of those simulations, the internal variability to the variations around that mean. I'm just going to be looking at the forced response. So the experiments I have are, again, the CESM1 large ensemble. There's 40 members. It's run with the CMIP 5 forcings from 1920 to 2100. The CESM2 large ensemble, which has 50 members, run with CMIP 6 forcings for the 1850 to 2100 time period. So I'm just going to be looking at this period of overlap from 1920 to 2100. Now, these are from the same model family, the CESM, but the models are considerably different. They differ across all components, the atmosphere, ocean, land, sea ice, and they have considerably different climate sensitivity, climate feedbacks, et cetera. So they're quite different models. So in order to be able to attribute differences between these large ensembles to model structure versus model forcing, we've run an additional set of simulations with the newer model, so CESM2, but using the older forcings, CMIP 5. We only have 10 members here because of computational considerations. We're actually in the process of running another 5. I'll also show some results from this CESM2 large ensemble, which has smoothed biomass burning emissions. So you saw that highly variable biomass burning and the fact that it changes over time. We've run an additional 50 members of the large ensemble, but that biomass burning has been smoothed over that 1997 to 2014 time period because it's been shown to be an important driver of differences in our climate transient simulations. Okay, so I can take this set of model simulations and now I can actually attribute the differences between CESM2 large ensemble and CESM1 large ensemble to model uncertainty, forcing uncertainty, and then this influence of biomass burning and the change in variability in biomass burning. Okay, so what does this look like? So just showing air temperature change for the first couple decades of the 21st century. This is what is simulated in the CESM2 model, large ensemble mean. And so, you can see kind of a classic anthropogenic fingerprint of climate change with polar amplification in the Arctic. This shows the differences between the CESM2 large ensemble and the CESM1 large ensemble. So basically showing that we have increased warming in the CESM2 large ensemble, warms considerably more over the 20th century. So what's shown below is the attribution of that to forcing differences, so this forcing uncertainty, and model differences, so the model structural uncertainty. And you see that this difference between these two models is purely a result of forcing differences. The CMIP6 forcing drives more warming than the CMIP5 forcing. The model is actually trying to counteract that. So if you attributed this difference purely to model structure, you're wrong. The model structure actually wants CESM2 to warm less. So what does this look like for sea ice? We're at a sea ice meeting, of course. Sea ice is near and dear to my heart. This shows the simulation of sea ice in the CESM1 large ensemble in green and CESM2 large ensemble in blue. And I'm just kind of highlighting the historical period here, so not the future projections. You can see that there is this mean offset. CESM1 has considerably more sea ice than CESM2. But it also looks like there's differences in the rate of sea ice loss at the end of this historical period. So we can highlight that by looking at the anomalies. And what you see is that indeed the CESM2 large ensemble has much more rapid sea ice loss. It then actually stabilizes, and this is in an ensemble mean of 50 members. This is not internal variability. This is a forced response. It stabilizes for about a decade or more and even rebounds a little bit. So we can again attribute this using our new simulations to model structure versus forcing uncertainty. What you see is that this really large sea ice loss, and actually this rebound as well, results from model forcing. It is not a model structural difference. It's just model forcing. Biomass burning, that highly variable biomass burning, accounts for maybe half of that signal. So what does this look like when we're thinking about sea ice sensitivity? So again, I showed you these two box and whisker plots before. Now we can include our simulations which have this newer model. The same model is shown in the black, but the forcing is shown in the gold. What you see is that if we use the same forcing, there's fairly small differences between the CESM1 and CESM2. And actually CESM2 has a weaker climate sensitivity than CESM1. It's even further away from observations than what we see in CESM1. And again, differences in biomass burning, as shown in the green, maybe account for about half of that signal. Just to note that this is not just a September sea ice phenomenon. This is something that we see throughout the year. So this is the CESM1 large ensemble in green, the CESM2 large ensemble in blue. And you see, again, CESM2 has much larger sea ice loss across months in terms of its northern hemisphere sea ice area. And again, that is largely driven by model forcing, as you see here. But in the winter months, the model structural uncertainty also drives larger sea ice loss in CESM2 than in CESM1. In September, it's fairly small. And there is some uncertainty bounds around these, which I'm not showing here because we only have 10 ensemble members in these CESM2 CMIP fibers. Okay, so CESM2 has larger ice loss than CESM1 throughout the year. This is largely driven by forcing uncertainty and the fact that CMIP6 forcing drives more sea ice loss. We can attribute that back to aerosol cloud interactions, at least in part, although we're looking into this further. So the model structure is modest, but if anything, it reinforces the sea ice loss. So The fact that we get larger ice area loss in the CESM2 large ensemble means that there should be a stronger surface albedo feedback, right? Sea ice loss leads to a surface albedo feedback strength, or affects the surface albedo feedback strength. But actually, that's not what we see in these simulations. There's all sorts of surprises that emerge in these runs. So what I'm showing here is the surface albedo feedback strength. I'm showing it as a function of latitude. So the zonally average, so the Antarctic, the Arctic. And in the Arctic, you see that the CESM2 model has a much weaker surface albedo feedback. You can see that when you look at the difference in the surface albedo feedback across the Arctic Ocean, shown here. So it has more sea ice loss, and yet the albedo feedback is weaker. So what's happening here? Oh, we can attribute this to model structural uncertainty. So whereas forcing actually causes a stronger albedo feedback in CESM2, as shown here, that forcing is consistent with the fact that CESM2 has larger ice loss. So forcing does drive a stronger albedo feedback, but model structure counteracts that. And so the model structural uncertainty, in this case, is what's responsible for this signal. So what's happening here? What does this mean in terms of thinking about model development needs? So we can go back to, what controls the surface albedo response? Of course, changes in ice area, losing bright white ice and replacing it with open ocean is going to have a big albedo hit, right? But changes in the albedo of the sea ice itself, melt ponds, as we heard just previously, also those kinds of factors can be important as well. And so in thinking about these differences between the CESM2 and CESM1 large ensemble in the early 21st century, it's not sea ice area that's controlling our surface albedo feedback. So because otherwise we'd have the opposite sign in terms of the differences between those two model simulations. So it must be changes in ice albedo. So what are the factors that control the ice albedo evolution? So this little schematic here kind of indicates the different things at play. So snow, the thickness of that snow, its distribution, its fractional coverage, episodic events, things like rain on snow events, snowfall in the summer, their impacts, ponding, as we heard in the previous talk, how ponds evolve, their fractional coverage, their depth, and their optical properties. And finally, timing is everything. The large sea ice losses that are being observed are largest in September. This shows the solar insolation. This is actually from the Shiba location. But the sun is low in September. It doesn't have a huge impact on the net shortwave budgets. So, if you're going to change your melt ponds in May and June, they might have a bigger impact, right? So when we think back to these differences between our models, the CESM1 and the CESM2, all of these things actually seem to be at play. This shows the snow climatology. This is from a recent paper by Melinda Webster from the CESM1 large ensemble and the CESM2 large ensemble simulations. And what you see is that CESM2 has just a much thinner snow. And you can see that in these histograms at the bottom as well. This smaller amount of snow results in a lower surface albedo. And we've done previous work that shows across CMIP5 models that if you have a lower albedo in your 20th century, you have less capacity for albedo to change. And so you actually get a weaker surface albedo feedback. So that's part of what's at play in looking at the albedo feedback between these two models, that they have very different snow climatologies. Part of the reason that we see that very extensive snow cover in the CESM1 simulations is because we have this large influence of episodic snowfall events in the summer. So this goes back to some work from Bonnie Light quite a few years ago now. This shows simulations from CESM1 of the surface albedo at a point at 82 north. So basically this location here. And this is just the time series from a number of different years and different ensemble members, just to indicate what's going on. So you can see in many years, you get an albedo evolution that looks very similar to what we observed. Bright, dry snow cover with a very high albedo. that snow starts to melt, that reduces the albedo. You then get ponding on the sea ice and reach these quite low albedo values before the snow covers, snow falls again. You get snow coverage and back up to this high bright albedo. So that occurs in a lot of years in the simulation, but there's many years in which it doesn't occur. So you can see these gray lines are all years at which the albedo never drops below about 0.7. So what's going on in those years in this model? It's the impact of these episodic snowfall events in the model. So basically we have, this is just showing for 1 point, just a sample time series. The albedo, kind of marching along at this high, bright snow-covered value. The melt season kicks in, you decrease your snow thickness. Ponds, which are shown in the black, start to form, and the albedo drops, and it looks like you're entering a melt season. You then get this episodic small snowfall event. It shades the ponds, it brightens the surface, and you jump back up to this very high snow-covered albedo. If you have the right sequence of those snowfall events, you get a couple in a row, like in this year, you basically never go into your melt season. So either in this model, we have too many episodic snowfall events, or the model is too sensitive to those snowfall events. But this is something that we need to consider in our model, in our climate model simulations, how we're dealing with the impacts of these kind of episodic small summertime snowfall events on the albedo. And finally, in CESM2, we find that even when we simulate a good albedo, we might be doing so for the wrong reasons. So this shows albedos as simulated in the CESM2 large ensemble. So the shading here is from different locations of the CESM2. So basically, the blue is from a mosaic sort of location. The red is from a Shiba location. And the solid lines are shown for the observational data from those two different field campaigns. Now, this is a free running climate model. And so there's internal variability here. So we don't expect to exactly get what was simulated or what occurred at Shiba or occurred at Mosaic. But it's good news that in general, the model looks like it's undergoing these stages of albedo evolution that you can see in observational data. However, it does so in spite of the fact that it has very extensive ponding on the sea ice. So this shows the pond fractions from the CESM1 and CESM2 model at these two different locations. So kind of hard to see the shading here, but there. And then what was observed in those field campaigns. And so you can see that, the albedos compare quite well, but the ponding is very different. So CESM2 has too many ponds relative to the observed state. We have evidence that those ponds are too bright. So the optical properties we're using in our model and our pond formulation are problematic. We're revisiting that as well. Okay, so to summarize, historical forcing uncertainty is sizable. It's something that we have to consider when we're looking across CMIP generations, so looking at different generations from the coupled modeling and comparison project, because we apply different historical forcings across those. It's also something that we have to consider when we're comparing to observations. CMIP 6 forcing, at least within the CESM2 model, drives increased early 21st century Arctic warming and also increased Arctic sea ice loss relative to the CMIP 5 forcing. In CESM2, the surface albedo feedback is weaker despite the larger ice area loss driven by the CMIP 6 forcing. And this highlights the importance of the simulated ice surface properties for our simulation of albedo and the simulation of the surface albedo feedback. And in our case, looking at these two different models, we see that the snow climatology, episodic snowfall events, and pond fractional coverage and the optical properties for those ponds are perhaps problematic and things that we need to revisit in our model developments. Okay, so with that, Got to show a polar bear, right? Anyway, I'll take any questions, and I'd like to leave up references too, because there's lots of them. But Bruno always asks the first question, isn't it? Mix it up a bit.
If we can have, we don't really need to ask questions. Okay, youngest or earlier career leader. All right. Don't be afraid to ask thinkers, you know, other people will know about, because they probably won't. Here, David, not sure if you count as early career or not, probably not.
Yeah, no, thank you. A fascinating talk, lots of interesting things. Question to the last figure with the melt ponds, obviously. How, I mean, probably the comparison of the observation of melt ponds on a one certain location, even if it's a moving location and over a long period, with modeled grid points is a bit of a tricky thing. How confident are you this is a general feature that the melt pond fraction is too high in the model and compared to observations?
So I think I agree with you. These are free running climate models. We're kind of just picking a point close to Mosaic. And so I do think this difference is pretty sizable, and I think it suggests we should revisit our ponding on the ice. And we're trying to do that actually using Mosaic data, looking at the controls on melt pond formation, like how much wet water runs off. And we do have some observations from Mosaic that can inform those kinds of aspects of our parameterization. I think what's more concerning here is that with this ponding, we get this albedo. Whereas in the observations, with this ponding, we get this albedo. And we have other evidence looking at the albedo of our ponds, that our ponds are too bright. So Bonnie Light is the one who developed the pond optical properties, and they were somewhat conservative in terms of that development. It's based purely on Shiba data, and there's indications that the ponds, the optical properties we're using for them within the Delta Eddington scheme of the CEIS model are lead to ponds that are too bright on average.
Bruno, no one can hear you.
Yeah, you have to have it.
I mean, I could leap in as well with 100 things to say on that point, but I'm holding my tongue.
So if you get a certain albedo, it means that the ice that's not ponded is also wrong. That means in the model, your ice is too bright, is too...
The bare ice albedo looks actually quite good. So we have, there's some comparison in Bonnie's recent Mosaic paper, albedo paper. The bare ice albedo doesn't look too bad. It's that our ponds, we have too many of them, but they're too bright. So, you know, even if you have a bare ice albedo that looks okay, your average albedo can be bright because of this compensation in the ponds.
So let me add, just mention in the pond schemes, there's several, as David mentioned, but what they tend to do is that you have a volume of melt pond and you can spread that out, in which case it's a larger area, but they're pretty bright because they're not so deep, or you can collect it into deeper melt ponds, which are darker. And so to me, the balance between, you know, whether they're spread out and shallow or collected and deep may be part of the difference here. And that's a tuning thing, but.
And the level pond scheme, I'm not sure how it's done in the topographic, but the relationship between pond area and depth is purely based on a relationship that was present during Shiba.
That's right.
So I
mean, it's empirical.
We developed that parameterization. It's like the ratio is 0.8. And it's because they were linear related in the Shiba data. That's one field campaign. Probably it might not be the right way to do this. So it suggests we need to revisit some of these things.
Well, you know, there's another scheme knocking around which does directly determine the area from the thickness distribution. So my
There's uncertainties in both.
There are uncertainties in both of them.
Yeah. And I think it's good we have different schemes and we can explore those uncertainties as well. But.
Right. There don't appear to be any questions online. I think we should probably move on to our next speaker now to keep approximately. Daniela, do you want to Okay, Daniela, you can't be heard. Algae. Algae is important, right? Because it affects optical properties. Okay, so algae is a property not probably very well characterized in many models at present, and that can affect the optical properties, which would directly affect the albedo for a given pond depth.
Yeah, and in CESM, we don't have algae. I mean, we don't even have it in the parameterization. We just ignore it. I mean, we don't simulate it, but we also, in Delta Eddington, you can just have an algal layer. We just ignore that as well.